Hello, and welcome to my presentation on fatigue failure mechanism in explosively welded metal composite containing tantalum, copper, and steel layers. My name is Szymon Derda, and I represent a research team from Opole University of Technology and Military University of Technology in Warsaw, Poland. I hope you'll enjoy this presentation. This slideshow includes several parts. Firstly, I want to talk about explosion welding process, composites subjected to the research, and the aim of the study. Then, I will describe the environment of fatigue testing and show the obtained results. Further, I will show primary crack origins identified in ruptured materials and their crack paths. Finally, I will share our conclusions. Explosion welding is defined as a solid-state process in which joining is accomplished by high-speed collision between two or more plates. Acceleration of the plates is a result of employing explosion energy during detonation of chemical explosives. The biggest advantage of the method is that it can be used to produce high-quality bond between metals which cannot be joined with the use of conventional methods. The short video and the pictures illustrate the basic idea of the process. The bond produced during explosion welding has a characteristic wavy form. Can it be a location of fatigue cracks? Let's see. Two metal composites are the subject of this study. In both cases, 1.5 mm thick tantalum layer was used for plating. In case 1, 1.5 mm thick oxygen-free copper layer was put between flyer plate and a P355 NL2 steel plate. In case 2, on the other hand, the thickness of the copper layer was 3 mm, and the material used for a base plate was 304L stainless steel. Each layer of the composite has its own unique task to perform. Tantalum, with its extraordinary corrosion resistance, prevents the degradation of a material even in highly corrosive environment. Copper allows proper heat dissipation during joining process, and steel base plate carry the load applied to the element. Several applications can be pointed out for such material: heat exchanger panels, chemical reactor vessels and columns, electrode plate drums, sheets and bonnets in tube heat exchangers. The aim of the study is to inspect the influence of the thickness of the copper layer on fatigue life of tantalum, copper, steel explosively welded composite. The methods used were the determination of the composite SN curve and the inspection of fatigue crack sites. Fatigue testing was carried out with the use of Instron electropulse E10000 presented in the picture on the bottom left side of the slide. Cyclic tension tests were performed with a loadings asymmetry ratio R equal to 0.02 in order to prevent buckling. Tests were carried out in ambient temperature with the loading applied parallelly to the interface of the composite. Tests were enriched by the interval inspection of the interface with the use of optical microscopy. A failure criterion was the complete separation of the material. On the right, you can see the geometry of the specimen used for testing. As the tests were carried out in a force-controlled manner, for easier comparison, a simple analytical model was used to assess maximum stress level in each particular composite layer. Several assumptions had to be made, such as uniform stress distribution, uniaxial state of stress, elastic strain range, continuous and flat surface of the interface. On the right, you can see basic force equilibrium equation, adjusted for the presence of 3 layers of the composite, and its transformation. The results were gathered in the presented table. You can see the name of all the specimens, maximum stress level in each layer, and fatigue life in cycles. The last column informs on the location of primary crack origin. Additionally, a pie chart was used for visualizing results from the last column. For the values of stress amplitude in tantalum under 415 MPa, all the primary cracks were identified in the tantalum layer. For the values of stress amplitude in tantalum over 415 MPa, primary cracks were observed at the interface of steel and copper layers or were not possible to be spotted due to major plastic deformation. A similar behavior was observed for case 2 at a higher stress level of 461 MPa. with the exception of one specimen which failed from steel and copper interface at a lower stress level. Almost 80% of the specimens failed in tantalum layer. Only 3 specimens failed due to crack originating in steel-copper interface. In the figure, you can see the maximum stress level in tantalum layer as a function of fatigue life. For each case, a linear regression line was drawn in a corresponding color. You can see that 2 data sets could be considered as one. Additionally, uncertainties of calculated stress levels were placed as error bars. Here, the example of specimen 2 from case 1, with the maximum load in tantalum layer of 356 megapascals and a fatigue life of nearly 260,000 cycles. In the picture, you can see a primary crack origin identified in the region circled with a red color. Crack paths were marked with white arrows. When we consider crack growth in the composite, we can find different behavior based on crack origin. It is not uncommon in explosively welded materials to encounter cracks which are not prone to propagate. As an example, in the picture you can see crack originating from steel-copper interface spotted at 350,000 cycles, which did not increase in size within the next 100,000 cycles. On the other hand, in the same specimen, a crack in tantalum layer was found at around 450,000 cycles, which propagated considerably within the next 50,000 cycles, eventually leading to final failure of the material at 515,000 cycles. The fatigue failure mechanism most commonly found in the considered material is shown in the picture. Severe fatigue damage lines in tantalum and copper layers appeared in the final stage of the specimen's life. Based on the conducted research, several conclusions can be stated. For case 1, at a maximum stress level below 415 megapascals, the fatigue cracks were initiated in tantalum layer. For stress higher than 415 megapascals, the primary cracks were initiated at steel-copper interface or were not identified due to severe plastic deformation. Similar behavior was observed for case 2 at a stress level of 461 megapascals, with the exception of one specimen which failed from steel-copper interface at a lower stress level. The thickness of copper interlayer and steel type have a negligible effect on the fatigue life of the composite. The fatigue performance of the tantalum layer and its interface with the copper determines the life of the composite. Interface investigation exhibited non-propagating fatigue cracks initiated at steel-copper interface. Thank you for your attention. I hope you enjoyed the presentation.